Ignition systems. This is what makes all the magic happen in an engine. We need to be able to light our air and fuel while it's under compression to make a good combustion burn, and the ignition system is what does that lighting via our spark plug. There are multiple different kinds of ignition systems. With the distributor style, we've got points, HEI, and magnetos, and for EFI stuff, we got waste fire and sequential. Points is our super old school style distributors. They've got a little capacitor inside of them that is what charges up, and then as the distributor rotates around, it makes contact. It sends power through, and when we get to our spark plug gap, it makes a spark. They can be finicky, they need to stay super clean. It's something that typically nobody's using anymore unless it's a completely stock OEM type setup. Now, magnetos fall into that as well. They're a very old school type of distributor. Aircraft used these a lot, as well as drag racing stuff back in the day. And actually, I think even Top Fuel Hemi stuff still use a magneto style because it makes one hell of a powerful spark. Speaking from experience, I've been hit by an aircraft one before when my hands were nowhere near anywhere they should have got spark, and it hurts like, well, let's put it this way, it went in right here and it came out my shoulder, and my entire arm was numb for several minutes, and it hurt like an SOB. So, gotta be careful with this stuff. They're like, you can really hurt yourself with spark on an engine. HEI is our most common one, and that's just going to the later GM style where the coil was built into the cap. You don't necessarily have to have the coil on the cap, but you've got a ignition module that's doing the stuff inside the distributor, and we've got a coil that we're supplying with power that makes the spark energy. And then with all of these, we've got a cap that's got a rotor inside of it that we're supplying in the power with, and as the rotor rotates and gets to another pole, it makes contact that connects our thing, and the spark goes off and heads to our spark plug. So that's why it's called a distributor, because it's just distributing the spark energy to the correct cylinder as this rotates. It doesn't know what cylinder it's actually firing to. It's just, all of a sudden, everything's making contact. The energy has somewhere to go. It has ground because of the spark plug being screwed into the cylinder head on the engine, and now the energy has somewhere to be released to, and that completes our electrical circuit for the split second that everything's lined up. EFI, on the other hand, whether it's waste fire or sequential, needs to be told what cylinders it's actually lining up with, because instead of having one single coil, like on a distributor, we have multiple coils. Now, the differential between the waste fire and the sequential is the sequential is going to have one coil per cylinder, versus the waste fire is one coil per 2 cylinders. And this works out where it's when you have cylinders that are opposite in the firing order. So if we've got our typical 1, 8, 4, 3, 6, 5, 7, 2, 1, 1, and 6 end up together, 8 and 5, 4 and 7, 3 and 2. so that we can have 1, 2, 3, 4 coils. Now it's called waste fire, and they're opposite in the firing order because it's going to be firing the coil when both cylinders are at TDC, or where we want to fire our ignition system prior to TDC. But one cylinder is ready to start its combustion cycle, and the other one is in overlap where both the intake and the exhaust valve are open. There's no compression, there's very little air and fuel in the cylinder. It's not going to ignite anything because the conditions to create a burn are not there. So we're just wasting the spark that's going to that cylinder because it's firing both cylinders at the same time. That's why we need half the coils. And in this case, we don't need to worry about where our camshaft is at. We just need to know where the crank is at to be able to fire it. Now, to be able to determine where it's at, we're going to have a crank sensor and cam sensor. Now, our waste fire system only needs to have a crank sensor versus for sequential we need a crank and a cam sensor. And the cam sensor is required to be able to tell the EFI which cylinder needs to be the one that gets fired. The crank sensor is just telling it where the crankshaft is in its rotation. So both of these are creating a relationship off of cylinder number 1. So when the crank says it's at cylinder number 1 and the cam says it's at cylinder number 1, we're able to decide when to fire based off of that. However, when the crank goes around and it says, hey, I'm at cylinder number 1 again after 1 revolution, the cam sensor says I'm not at cylinder number 1, so it knows that it needs to fire the next one in the order, which would be cylinder 6 like we were talking about. And then when it goes around again, it says, hey, I'm at number 1, hey, I'm at number 1. It knows it needs to fire number 1 again. Now with the waste fire system, we wouldn't need the cam sensor, and instead we could get away with just the crank sensor, but it probably needs to be a crank sensor like this, where we've got our, this would be a 60 minus, or well, this one's a 36 minus 1. There's also 60 minus 2 wheels. This is just for a Hall effect sensor, where as it goes past, it gets a signal, hits the gap, it loses signal, it gets a signal, it loses signal, and it creates a electrical wave in the line. Well, when we get to a point where there's this extra gap, that extra gap is when the EFI can decide that, hey, we're starting our cycle right now, and it can count then 1, 2, 3, and if we say number 1 is at number 4 of the teeth after the gap, then the crank sensor is able to tell the EFI that, and we can program it so that it sees a blank, 1, 2, 3, fires on 4 kind of a thing. And then because it's an even number of teeth all the way around, the EFI can interpret where the next 3 cylinders are as well to fire 4 cylinders off of 1 revolution. This is a good system. It's accurate. The hard part here is this is all aftermarket stuff you have to add to an engine if you're going to be doing this and not using a engine that came with a crank or cam sensor from the factory. Now if we want it, we can add a cam sensor to our conversion, either via a similar Hall effect style sensor if we can access through the timing cover. And we can have something as simple as a little wheel in there, or just a pin where when it comes around it sees it once a revolution on the camshaft kind of a thing. It could also be added somewhere else along the camshaft if that's an availability thing. It really depends on what somebody's willing to fab or come up with. Or the simple solution is we can gut out a distributor, and there's a pickup for the distributor inside that also has places where it counts cylinders, and the conversion for that is there's on a V8 there'd be 8 of them. We can grind 7 of the teeth off so we have a single one. That becomes our number 1 indicator in our distributor, and we've converted our distributor into a cam sensor. At which point we're not using any of the rest of it. We can eliminate the cap that sends the spark plug wires, and we can just put a blank on there, because we'll be using individual coils to fire our cylinders at that point. Now, why is the timing important? Well, when we've got our cylinder and our piston is traveling upwards in that cylinder, and we're compressing our air and fuel up here in our cylinder head, we've got our spark plug. So we've got all our air in here. And our fuel. We're starting to create the conditions that are ready to make good combustion. Now, our timing is important because are we firing it only when this piston reaches TDC? TDC being top dead center. That's going to be at a height here. Air and fuel burn. They don't explode. And the differentiation between that is an explosion versus a burn have drastically different rates at which they expand, or the flame front travels. So when this spark goes off, it takes time for the flame to travel. So it's gonna make a little kernel of spark there. And if we broke it down with like a high-speed camera, it's gonna start out with something like that with each frame of the camera, where it fires and then it's just a little bit at a time, because gasoline actually burns fairly slow. So why this is important is we need to time that burn to our piston for maximum pressure that we can utilize when the piston's in the best part of its power stroke. So that's when it's starting to go back down. We want max cylinder pressure as that piston is starting to go back down. If we get this max cylinder pressure after it's too far down, we've wasted the pressure, because that pressure wasn't being built up where it could apply the most force to the piston and therefore put that power into our rotating assembly. If we apply it too early, it might create max cylinder pressure before the piston is at top dead center, and it's actually going to try to force the engine to go backwards. Now, because it's running and moving and it's got the momentum of it, it might still get up past top dead center. But now we've got all of that pressure there, and up near top dead center, because of the swing of our crankshaft, the piston is slowing down, and it's like not moving up and down hardly at all near top dead center. So now there's all that pressure, and it's literally has nowhere to go. So as it burns and then it starts to finally go down again, a lot of the energy might get dissipated before it even starts pushing on the piston. And what we're also doing is by creating that too early in the cycle, it's just, like I said, if it's still coming up, it's just starting to fight itself. But even before we reach max cylinder pressure, like even if that was right at top dead center, and we have maximum pressure to push down the piston when it's going, it was still building pressure, because as the burn starts, it's going to increase pressure in the cylinder, because the more it burns, the more pressure it's making. And then at some point we've reached our max pressure, and then the piston's starting to travel down again, and that pressure is going to fall off with the piston going down. So because of this building of pressure here, as the piston's coming up and this pressure is still building because we've already fired and is burning, all of this can be fighting that piston coming up. So we need to find the ideal point of ignition where the piston is getting to TDC, where we're not building a ton of pressure that's fighting it to get to TDC. But then after it reaches TDC, we're getting our max pressure where the piston's starting to travel back down, so we can best utilize that pressure to move the piston. And that's where I was talking about this window. There's a window in here where, you know, piston near TDC, it's not moving a whole lot. But then we get into where it starts to move a lot, where we're getting our power stroke cycle. That's where we want to utilize that pressure and use it as best that we can before the exhaust valve starts to open as the piston gets towards the bottom. So this is why timing is important, because too early is a very big problem, and too late it can also be a very big problem, because it might be to the point where it won't even idle, because your max cylinder pressure is completely wasted because the piston's too low in the cylinder already because it's traveling down, or the exhaust valve opens up and it's still got a bunch of pressure that just gets wasted and blown out the exhaust. So this is very important, and determining what your timing should be is not something you can just do. You can get close. There's plenty of ballpark figures out there to get you close. But if you want to know what the perfect ignition timing is, you have to dyno the engine, because the engine will tell you what it wants. Because if you're going in the right direction, it will increase in power. If you're going in the wrong direction, you will lose power. And not all engines are made the same. I have seen engines where being 2 degrees under was down 2 horsepower. I've seen, and then ideal was best power, and 2 degrees over would be too much ignition timing, too early in the cycle, too advanced, was down 10 horsepower. And from this, it should be pretty clear that being a little bit less timing than ideal is a hell of a lot better than being a little too much over ideal, because being too advanced, which is that building that pressure where it's fighting the piston coming up, is significantly more detrimental than being a little bit behind. But because this pressure curve is like this in the cylinder, you know, we're looking at the difference between a lot of pressure fighting the piston coming up versus a little pressure at the end of the cycle pushing a little bit extra on the piston. And this is not the case in all engines. This is one specific case where I was trying to test this and find out. And I would typically test this on every single engine that I would dyno because I wanted to know what the best timing was. And usually we'd move it around, we'd start low on the timing and do a few pulls, and each time we did a pull, we'd add a degree or two of timing until we found our best power. And if we added more, we'd either see it lose or we'd see it wouldn't change. Now, one engine in particular was it was a 360 Mopar stroker that we did, and between 28 degrees and 36 degrees of ignition timing, it made the exact same power. It didn't care. And that one had a pretty healthy cam on it, but this is not normal. This is a absolutely massive timing window where the engine just didn't care because, I don't know, I mean, if I'm going to take guesses as to why that was, it would be that at 28 degrees or 36 degrees, we weren't hurting it before the piston got to top dead center as far as the combustion burn of that. And we were utilizing almost the entirety that we could in the power cycle. Or what was happening was we were at a point where the trade-off here, when the exhaust valve opened versus where it was fighting the piston on the way up, was so close in that we were, whatever we were gaining on one end, we were losing on the other, and it just didn't care. But that being said, when you've got a situation like this, there 28 degrees is what we set that engine at. Because we're not gaining anything by more ignition advance. All we're doing is increasing the pressure that that piston has to fight getting to TDC. And since there's no power gain by increasing the timing, it was kind of pointless to do that because we knew that pressure was increasing here even if we weren't gaining any power on the other side. Like, why make the rotate assembly fight that pressure? Like, it's making the engine less safe, or just putting more stress on the engine even though the power wasn't changing. So you take the least amount of timing required to make the engine make best power. Now, our coils. When we're working with the distributor setup, we've only got the one coil, and what a coil is doing is it's taking your 12 volts from your battery, and the coil's job is to convert that into a much, much higher voltage. So we're taking our 12 volts and we're turning it into, say 40,000 volts. And that's what gives us that energy to make that spark. Now, because to do this, the coil has what's called a dwell cycle. And this is just basically like the recharge time required for it to be able to be ready with that 40,000 volts to fire the next cylinder. Now, because that takes time to charge up, that's where going to a coil on plug or coil near plug setup comes into play, especially with super high power, high cylinder pressure stuff, or high RPM things, because as soon as this dwell time isn't met at higher RPM, it doesn't have time to recharge completely, so our ignition power can fall off. So by going to a coil on plug or coil near plug, we can give either each individual cylinder or 2 cylinders per coil, that the charge time stays longer, because instead of 1 coil for 8 cylinders, we can do a waste fire where now we've got 4 coils for 8 cylinders, or a coil on plug or coil near plug, we've got 8 coils for 8 cylinders. So you can imagine that as the RPM increases, the number of times that a single coil has to fire for 8 cylinders at 7,000 RPM is a lot. And we can cut that to a quarter simply by doing a waste fire system. Or we can cut that to 1/8 of that by doing a coil on plug or coil near plug, so that it allows the dwell time to be able to fully recharge that coil so that we have maximum spark energy when that cylinder comes around, even at high RPM. And this becomes more important because as we get into boosted applications or just high compression or anything like that, the cylinder pressure itself makes it harder to make that spark happen. And that can be referred to as spark blowout, where especially on a turbo like the boost level just gets to the point where the spark energy literally gets blown out before it can ignite the air and fuel, because it just does not have enough energy to get it lit. Typically, when anybody will run into that type of a problem on the dyno, you start tightening up your spark gap, because the size of the gap matters too, because it takes a lot more energy to jump this gap the bigger it is. The smaller it is, the easier that jump can be made to create that spark. However, when it's a bigger gap and we can definitely make that jump, we have a bigger arc happening between, or a bigger spark happening, which then has the ability to make a better burn, because it's kind of like trying to start a campfire with a match versus with a propane torch. Bigger should get it going faster. Now, because of that disadvantage that the distributors have, we've got ignition boxes. Now, an ignition box just gets added into the system, where it's wired in to the coil, and the ignition box is what gets power from the car. Now, typically what an ignition box is going to do is it's going to increase the input voltage to the coil. So instead of it getting just the 12 volts, we're giving the box the 12 volts, and the box can give the coil a couple hundred. So let's say we're going to a 500 volt input on that coil. Well, now because that voltage is so much higher to begin with, the output voltage, because our 12 was turning into 40,000, we can then have a multiplier where this 500 input voltage becomes whatever, even more. It ends up being like I don't know what the actual number would be, but something in the millijoules. So we've increased to just a crazy high number of voltage to make a very, very, very strong spark. Also, that's going to help alleviate some of the problem with the dwell cycle when we get into our high RPM, because we have such a much stronger spark right off the bat, that when it starts to taper off at high RPM, we're still so much farther ahead of what we were in spark charge that it really becomes a non-issue. The other thing that an ignition box do that's super cool is multiple sparks. Now, this is not the case at high RPM. I think typically this is under 3,000. But instead of having just a one single spark, it will fire the spark plug 3, 5, I think up to 7 times per engine cycle per cylinder. And this is really kind of crazy, but it should give you an idea of, because it's just charging that coil so fast, the fact that it's able to fire the same cylinder multiple times during the same compression or same power cycle. It's cut down the dwell and charge time on that coil so much where it's still able to provide a good spark that's why when it goes up in RPM and then it goes back to single spark, we've still got plenty of ignition power to be able to fire that cylinder. Ignition boxes can come with a bunch of other features too, like rev limiters, ignition retard based on either RPM or boost level, or just other features related to the ignition system that can be built into the boxes that are super handy. Or in the case of an EFI setup where maybe you're still using a distributor, the ignition box will talk to your EFI for you, and your EFI back to your ignition box, where you've got something where the distributor is telling the EFI the RPM and stuff, which then sends the signals to the box to then tell it how and when to fire, so you can get those multiple firings even though before it goes to the coil, which then goes back to your distributor to then actually get told which cylinder to go to, where it kind of creates a feedback loop out of the system that way. Now, obviously, especially when we get into the EFI stuff, every engine ends up being a little bit different, especially on OEM ignition systems, just because sensors can be all different. How and where they get that signal from can be all kinds of different. Typically, though, it's going to be some kind of sensor on the crankshaft, some kind of sensor on the camshaft, although that can vary based on the engine. There's also, even within the LS series, there's different reluctor wheel tooth numbers. So you have to know what that is for your engine to start with if you're buying an aftermarket fuel injection system, because that means the sensor is probably different, as well as this, because it is different, the signal going to the EFI is going to be different. Now, a lot of the aftermarket ones, they'll be programmable, but you still need to know what you have in your engine to begin with. So we're not going to get into a whole lot of that. This is just kind of a quick overview of the ignition systems, because everything can be so much different. So we talked about the ignition box. No, that is not required, because there's distributors that will run an engine that don't have an ignition box, and there's ones that do have an ignition box. It's just kind of an add-on feature, especially for racing and high performance applications, where it's really kind of a good or nice thing to have, especially if you're talking about boost or high compression, where we're talking about that spark blowout. You need to get that spark energy up in order to make it work, and the ignition box is a super easy add-on to the system that gives a huge increase of spark energy without having to do all of the work of going to coil on plug or coil near plug and have the requirement of an EFI system where the distributor can work just fine all on its own with a carburetor, and you don't need a computer to run it. So which system is best for you entirely depends. I'm going to be a proponent that if you're going EFI anyway on your engine, you might as well make it control the spark as well. It just makes sense, and there's plenty of kits out there where you can just buy the components that talk to your EFI system, and it's all kind of a plug and play setup where it makes it easy. And then the best part is that now, once you have it initially set, even if you're using a distributor style and you initially get that distributor set, you don't ever have to move anything physically on the engine again, because it can all be controlled via the computer, which makes it super easy once you get to the dyno, where it can be just a couple of highlights and clicks and you've changed your ignition timing, instead of doing the old school thing with distributor where you got to get underneath the hood, you got to unbolt it and turn it a little bit and tighten it back down and check it with the timing light to make sure it is what you set it to. You can eliminate all of that after the initial thing when it's controlled by the computer. which makes it super easy and handy and very quick turnaround to make multiple dyno runs to really dial in your ignition timing easily. Overall, ignition system is, I mean, it's just one of the things that's kind of required. It can be super simple or it can get more complicated, but the point is that it's all about having good spark. Because it's important to making sure you get your air and fuel lit off efficiently and starting a clean burn to make sure you have best power from it. If your spark's weak, you run into trouble. So anyway, that's our quick little overview for this classroom on the ignition systems. You know, everything's a little bit different and you just got to keep that in mind. And you know, depending on your build, you'll have to decide which type of ignition system that you want and or need to go with. And it's kind of just gonna set itself up for you, especially, you know, because if you're ending up EFI, it's kind of a no-brainer. You want that to be controlled with that. If you're carbureted, you have, you know, the option, but are you really going to add a ton of complication of having a computer controlling individual coils for your cylinders when you're still carbureted and not doing that with the fuel? Like, it, you know, each style system has its place and has its, you know, pros and cons because of that. But largely, this is something you're probably not going to think about a whole lot, but you should be keeping in mind should you be deciding that maybe you're carbureted right now, but in the future you want to go to EFI. It's going to be something to keep in mind about whether or not you'll be able to reuse any parts or whether everything's just going to be a complete individual system on its own, and when you convert, everything gets converted with it. So just things to consider. I don't expect a whole lot of you know, time to be spent on the ignition system as far as, you know, planning out a build, because it's going to kind of be a given for you.